201.6 million years ago, one of the 5 greatest mass extinctions in the history of this planet took place. 80% of all species disappeared. For decades, scientists were certain the cause was heat, massive carbon dioxide emissions, a runaway greenhouse effect, suffocating warmth. In 2024, a new study of mercury preserved in ancient rock overturned that entire picture. It turned out the cause was not a greenhouse gas. The cause was darkness, a volcanic winter so severe that it altered the entire trajectory of life on Earth. And it was this cold, strangely enough, that spared the animals who would soon become the rulers of the planet for the next 135 million years. This is the story of how cold created the reign of the dinosaurs. Before we go any further, please subscribe to this channel. Your support genuinely helps us keep making films like this one. Thank you. Now, let's go back to a world you would not recognize as Earth at all. 205 million years ago, there was no Atlantic Ocean. There was no Pacific Rim of Fire as we know it today. No separate continents drifting independently across a blue globe. There was one landmass, Pangea, a single colossal supercontinent stretching from pole to pole, so vast that its interior deserts extended for thousands of kilometers in every direction, so far from any ocean that no rain-bearing wind could reach them. If you had stood at the heart of that continent, the nearest coastline might have been 2,000 kilometers away, in any direction you chose to walk. This was the late Triassic world, and it was not a world of dinosaurs. That is worth sitting with for a moment, because it inverts almost everything popular culture has taught you to expect. Dinosaurs existed during this period. The first true dinosaurs had appeared roughly 30 million years earlier. Small, bipedal, unremarkable creatures scattered thinly across the landscape. But they were not in charge. They were not even particularly successful. The Triassic world belonged to a different group of reptiles entirely, the pseudosuchians, a lineage that would eventually give rise to modern crocodilians, but that in the Triassic had diversified into forms far stranger and far more dominant than anything alive today. Picture massive armored herbivores called Dinosaurs, built like tanks, covered in bony plates, rooting through the undergrowth with pig-like snouts. Picture Rauisuchians, bipedal and quadrupedal predators, some reaching 6 meters in length, with skulls built for crushing bone, occupying precisely the ecological role that large theropod dinosaurs would later fill. Picture Phytosaurs, crocodile-shaped ambush predators lurking in Triassic rivers, so convergent in body plan with modern crocodiles that early paleontologists sometimes confused the two, despite them being separated by 200 million years of independent evolution. This was a world engineered, ecologically speaking, by the crocodile-line reptiles. Dinosaurs were a minority presence, tolerated at the margins. To understand how strange this arrangement truly was, it helps to walk through the late Triassic world in more detail, because almost every assumption a modern viewer carries about which animals belonged at the top of the food chain in the age of reptiles turns out to be wrong when applied to this particular period. Start with the Dinosaurs. These armored herbivores, some reaching 3 meters in length, were covered from neck to tail in interlocking bony plates called osteoderms, arranged in neat rows across their backs and flanks, in a pattern that gives their fossils an almost architectural regularity. Some species carried long, forward-curving spikes projecting from their shoulders, structures that likely served both as defense against predators and, quite possibly, as display features used in competition between individuals of the same species. They rooted through Triassic soil with specialized upturned snouts, probably digging for roots, tubers, and buried invertebrates in a manner ecologically similar to a modern pig, despite belonging to a reptilian lineage with no close relationship to any living mammal. Apatosaur fossils are found across the globe, from what is now Germany to Argentina to the southwestern United States, indicating a lineage that had achieved genuine worldwide distribution across the interconnected landmass of Pangea. Then there were the Rauisuchians, and here the ecological role reversal with later dinosaurs becomes almost impossible to ignore. Animals like Postosuchus, found in Triassic rock formations across North America, walked on 4 limbs but could likely rear onto 2 when pursuing prey, possessed a skull built with the same basic engineering principles that would later define large theropod dinosaurs: deep, laterally compressed, packed with serrated, blade-like teeth designed for slicing through flesh and, in some cases, crushing bone outright. Some Rauisuchian species reached 6 meters in length, roughly comparable to a mid-sized theropod dinosaur from tens of millions of years later, and functioned as the apex predators of their ecosystems in essentially the same way Allosaurus or Tyrannosaurus would eventually function in the Jurassic and Cretaceous. If you had been dropped into a late Triassic landscape with no prior knowledge of vertebrate paleontology, your instinct, watching a Rauisuchian stalk a herd of apatosaurs across a floodplain, would almost certainly have been to assume you were looking at a dinosaur. You would have been wrong, and the mistake would have been entirely reasonable, because evolution had independently arrived at a strikingly similar predatory body plan twice, in 2 different reptilian lineages separated by tens of millions of years. The phytosaurs complete this picture of a world already thoroughly rehearsing through an entirely different cast of characters. The ecological roles that crocodilians and, later, dinosaurs would eventually make famous. Long-snouted, heavily armored, built low and wide for a life spent mostly submerged in Triassic rivers and floodplains, phytosaurs are so convergent with modern crocodiles in overall body shape that the most reliable way to distinguish a phytosaur skull from a crocodile skull, even for a trained eye, is the position of the nostrils. Set far back near the eyes in phytosaurs, positioned at the very tip of the snout in true crocodilians. This is convergent evolution operating with almost mischievous precision. 2 entirely separate reptilian lineages, one ancient and now completely extinct, one still swimming in rivers today, independently discovering that the same basic body plan solves the same basic ecological problem of ambush predation in slow-moving fresh water. Beyond these 3 dominant groups, the late Triassic supported an extraordinary supporting cast. Giant amphibians called metoposaurs, some with skulls approaching a meter in length, patrolled shallow lakes and rivers with a body plan that had changed remarkably little since their ancestors first crawled onto land more than 100 million years earlier. Early mammal relatives, small, nocturnal, insect-eating creatures barely larger than a modern shrew, scurried through the undergrowth, occupying an ecological niche defined almost entirely by the need to avoid the attention of everything larger than themselves. Tree-dwelling reptiles with an extraordinary gliding membrane stretched between elongated ribs, structurally unrelated to the wing membrane that pterosaurs would independently evolve, coasted between the towering conifers and cycads that dominated Pangea's forests. And the climate itself deserves attention, because it shaped everything happening within it. The interior of Pangea, situated at the heart of the largest landmass this planet has ever assembled, experienced a monsoonal climate of genuine extremity. Brutally hot, arid conditions for much of the year, punctuated by intense, concentrated seasonal rainfall, driven by the same basic atmospheric physics that produce monsoon systems in modern Asia, but amplified by the sheer, unprecedented scale of the continental interior, generating and modifying its own weather patterns. Fossilized soil horizons from this period preserve clear evidence of this extreme seasonality. Deep desiccation cracks from prolonged drought, overlain by sediment deposited during subsequent flash flooding, repeating in cyclical layers that record the same brutal wet-dry rhythm playing out year after year for millions of years across the supercontinent's vast interior. This was the world then, at the moment the crust beneath it began, imperceptibly at first, to stretch. And there was one more detail about this world that mattered more than anyone at the time could have possibly understood. Some dinosaur populations had already pushed toward the poles. Fossil track sites in what is now the high latitudes of the ancient supercontinent, regions that, even in the warm greenhouse climate of the Triassic, experienced genuine winter darkness and seasonal cold, preserve evidence that small dinosaur species were living and breeding in these frigid margins, adapted to conditions that the heat-loving giants ruling the tropical heart of Pangea had never needed to tolerate. This detail is the hinge on which the entire story turns. Keep it in mind. We will return to it. For millions of years, this arrangement held. The Rauisuchians hunted. The Itosaurs grazed. The Phytosaurs waited in the rivers. And deep beneath the supercontinent, in the solid rock of the mantle, something else was happening. Something with no relationship whatsoever to biology, driven entirely by the internal heat engine of the planet itself, that would eventually bring this entire ecological order to an end. Pangea was beginning to tear apart. The forces responsible are the same forces responsible for every supercontinent breakup in Earth's history. The same plate tectonic engine driven by heat rising from the planet's core through the mantle that has assembled and dismantled continental landmasses again and again across 4.5 billion years. Beneath the future boundary between what would become North America, Africa, and South America, mantle plumes, vast upwellings of abnormally hot rock rising from deep within the Earth, began to concentrate. As this hot material pushed upward against the base of the continental crust, the crust itself began to stretch, thin, and fracture, in the same way a piece of taffy thins and eventually tears when pulled from opposite directions. Where the crust thinned enough, magma found its way to the surface. And what began as scattered volcanic activity along a developing rift zone would, over the following 600,000 years, become the single largest outpouring of lava this planet has ever produced in its documented geological history. A continental flood basalt province so enormous that geologists eventually gave it a name matching its scale: the Central Atlantic Magmatic Province, commonly abbreviated as CAMP. It is worth pausing on the mechanics of continental rifting itself, because the process that eventually produced CAMP did not begin as anything visibly dramatic. Rifting starts slowly, almost imperceptibly, with the thinning of continental crust over a span of millions of years before any lava reaches the surface at all. As mantle plumes concentrated beneath the future boundary of the Americas, Africa, and Europe, the crust above them began to stretch laterally, thinning from its ordinary continental thickness of roughly 40 kilometers down toward the much thinner crust, characteristic of ocean basins. This thinning produced a network of extensional fractures, normal faults in geological terminology, along which blocks of crust gradually dropped relative to their neighbors, creating elongated rift valleys strikingly similar in overall form to the modern East African Rift Valley, itself an active, present-day example of exactly this same tectonic process still unfolding today, more than 200 million years after Pangea's rifting began. For a considerable span of time, perhaps several million years, this rifting proceeded largely without volcanism, producing broad, shallow sedimentary basins that filled gradually with river and lake deposits, eroding off the elevated rift shoulders on either side. Fossils recovered from these earliest rift basin sediments, including, notably, some of the very Triassic dinosaur trackways and early dinosaur bones found in the Newark Basin of the eastern United States, record the ecosystem functioning essentially normally, the ordinary late Triassic cast of etosaurs, phytosaurs, and Rauisuchians going about their lives in river valleys that, unknown to any of them, were the opening act of a supercontinent's dismemberment. The transition to active volcanism, when it came, appears to have been comparatively abrupt. As the crust thinned past a critical threshold, decompression melting began in the underlying mantle, a process in which mantle rock, already extremely hot but held solid by the immense pressure of overlying crust, begins to melt, not because it gets any hotter, but because the pressure holding it in a solid state is released as the crust above thins and weakens. This melted mantle material, less dense than the solid rock surrounding it, rose buoyantly toward the surface, accumulating in vast magma chambers before eventually breaching the surface through fissures, sometimes stretching for many kilometers in length, rather than through the single central vent most people picture when they imagine a volcano. This fissure-style eruption is characteristic of essentially every large flood basalt province in Earth's geological history, and comparing CAMP to its most famous relatives helps calibrate exactly how extraordinary an event it truly was. The Siberian Traps, erupting roughly 252 million years ago, and closely associated with the end Permian mass extinction, the single most severe extinction event in the entire history of complex life on this planet, covered an estimated 2 million square kilometers, a genuinely staggering figure in its own right, yet still only a fraction of Camp's documented 7 million square kilometers. The Deccan Traps of India, erupting around the time of the Cretaceous-Paleogene boundary, 66 million years ago, and long debated as a potential contributing factor alongside the Chicxulub asteroid impact in the extinction of the non-avian dinosaurs, covered roughly 500,000 square kilometers at their original extent. Measured purely by aerial footprint, Camp dwarfs both of these far more commonly discussed flood basalt provinces by a considerable margin. And yet it remains, even among dedicated paleontology audiences, comparatively obscure, overshadowed perhaps by the fact that the extinction it caused, however severe, did not carry the same cultural weight as the death of the non-avian dinosaurs, and occurred at a boundary between two periods, whose names, Triassic and Jurassic, carry far less immediate recognition for most people than Cretaceous and Paleogene. The magma that fed Camp's eruptions was tholeiitic basalt, a specific chemical composition of lava characterized by relatively low viscosity, meaning it flowed readily across the landscape, rather than building the steep, cone-shaped volcanic edifices associated with more viscous magma types. This low viscosity is precisely what allowed individual lava flows within Camp to travel extraordinary distances from their source fissures. Some documented flows extend for hundreds of kilometers, spreading across the landscape in thin, extensive sheets, rather than piling up locally, which is part of why a single eruptive event could blanket such an immense total area. Successive flows, separated by intervals of quiescence, lasting anywhere from years to millennia, gradually built up a layered stack of basalt that, in the best preserved sections still exposed today along the cliffs of the Palisades in New Jersey and New York, reaches thicknesses of several hundred meters, a physical, climbable, touchable record of an eruptive sequence that fundamentally reshaped the trajectory of life on Earth. Let's be precise about the scale involved, because approximate language does not do justice to what actually happened. Camp is the most extensive continental flood basalt province ever identified on Earth. Its remnants now scattered across 4 continents by the very same continental drift the eruptions helped set in motion, preserved today in the eastern United States, in Morocco, in Brazil, in parts of Europe. At its full original extent, before erosion and continental separation carried pieces of it thousands of kilometers apart, Camp covered more than 7 million square kilometers. To put that number in a form the mind can actually hold, 7 million square kilometers is larger than the entire land area of Australia. It is larger than the combined area of India and Western Europe. If you tried to lay that much lava across the state of Texas alone, you would need to stack it more than 16 kilometers deep to account for the total volume erupted across the province as a whole. This was not a single eruption. It was not even a single volcano. In any sense, a person standing on the ground at the time would have recognized. It was a sustained, repeated sequence of eruptive pulses. occurring across multiple separate volcanic centers spread over an enormous geographic area, continuing on and off for roughly 600,000 years. A span of time that is, in human terms, essentially unfathomable, but that in geological terms represents a startlingly compressed, intense episode. 600,000 years to erupt millions of cubic kilometers of lava is fast. It is catastrophically, planet-alteringly fast. And the eruptions did not simply produce lava. They produced gas, enormous quantities of it, injected directly into the atmosphere with a violence and a persistence that modern volcanic eruptions, even the largest ones in recorded human history, cannot fully prepare you to imagine. This is where the story, for decades, seemed settled. Geologists have understood since at least the 1980s that the timing of the camp eruptions and the timing of the Triassic-Jurassic extinction line up with remarkable precision. The eruptions begin, and within a geologically brief window, somewhere between 80% and possibly more of all species on the planet disappear from the fossil record. The causal relationship was never seriously in doubt. What remained genuinely uncertain for the better part of 4 decades was the specific mechanism. Volcanic eruptions of this scale release both carbon dioxide and sulfur dioxide simultaneously, and these two gases, once in the atmosphere, do almost exactly opposite things to a planet's climate. Carbon dioxide is a greenhouse gas. It traps outgoing infrared radiation, and given enough time and enough volume, it warms a planet, sometimes dramatically, sometimes for a very long time afterward, since CO2 can persist in the atmosphere and ocean system for tens of thousands of years once released. The conventional explanation for the Triassic-Jurassic extinction, accepted by most researchers for decades, followed directly from this chemistry. CAMP. The reasoning went, pumped a colossal volume of carbon dioxide into the atmosphere over its 600,000-year eruptive history. Global temperatures rose. Ocean chemistry shifted as the seas absorbed excess CO2 and became more acidic, undermining the ability of marine organisms to build calcium carbonate shells and skeletons. The land baked under intensified greenhouse conditions. Ecosystems collapsed under sustained heat stress, both on land and in the ocean. This was, for a very long time, simply what the Triassic-Jurassic extinction was understood to be: a slow-motion greenhouse catastrophe, unfolding gradually across hundreds of thousands of years as carbon dioxide steadily accumulated and the planet steadily cooked. It made intuitive sense. It fit the known chemistry of volcanic emissions, and it aligned with what researchers already understood about other, better-studied mass extinctions in Earth's history, where sustained greenhouse warming from flood basalt volcanism, most famously the Siberian Traps eruptions at the end of the Permian period, tens of millions of years earlier, appeared to have played a central role in ecological collapse. But there was a second gas involved in these eruptions, one that behaves nothing like carbon dioxide, and one that researchers had for decades treated as a secondary player in this particular story, present certainly, but not decisive. Sulfur dioxide, once injected into the atmosphere in sufficient quantity, does not warm a planet. It cools one, sometimes with startling speed, sometimes with an intensity that dwarfs the warming effects of carbon dioxide released during the exact same eruptive event. When sulfur dioxide reaches the upper atmosphere, it reacts with water vapor to form sulfate aerosols, microscopic reflective particles that scatter incoming sunlight back into space before it ever reaches the surface of the planet. This is not a hypothetical mechanism. It has been directly observed in real time within the span of modern human history. When Mount Pinatubo erupted in the Philippines in 1991, releasing roughly 20 million tons of sulfur dioxide into the stratosphere, global average temperatures dropped by approximately 0.5 degrees Celsius for the following year. A measurable planet-wide cooling event triggered by a single eruption that, by geological standards, was almost trivially small. Now hold that number. 20 million tons of sulfur dioxide from Pinatubo, against what researchers eventually discovered had been released during the earliest, most intense pulses of camp volcanism. The breakthrough came from an unexpected direction, not from studying lava directly, but from studying mercury. Mercury is released by volcanic eruptions and, crucially, by very few other geological processes at comparable scale. When large volcanic events occur, mercury vapor is injected into the atmosphere alongside sulfur dioxide and carbon dioxide, where it eventually settles out and becomes locked into sediments accumulating on ocean floors and in ancient lake beds around the world. Sediments that, hundreds of millions of years later, become the sedimentary rock layers that paleoclimatologists can now sample, slice, and analyze with extraordinary chemical precision. A spike in mercury concentration within a specific rock layer is, in the language of modern geochemistry, essentially a fingerprint of intense volcanic activity occurring at that precise moment in time. A signature independent of the lava itself, preserved in locations that may be thousands of kilometers from where the eruptions actually took place. The recognition that Camp and the Triassic-Jurassic extinction were connected did not arrive all at once. And the history of how researchers pieced this story together across more than a century deserves its own attention, because it illustrates how long it can take for a genuinely coherent picture of an ancient catastrophe to emerge from scattered, initially unconnected observations. The basalt cliffs of the Palisades, rising dramatically along the western bank of the Hudson River across from Manhattan, had been studied by American geologists since at least the early 19th century. Though for most of that period, the rock was understood simply as a striking local geological feature, rather than as evidence of a continental-scale catastrophe. Similar basalt formations were independently documented across the eastern United States, in Morocco, and eventually in Brazil and West Africa. But for decades, these occurrences were treated largely as separate regional phenomena, their shared origin obscured by the simple fact that the continents containing them had, by the time geologists began seriously studying them, drifted thousands of kilometers apart from the positions they occupied when the lava first erupted. The recognition that these scattered basalt provinces, represented pieces of a single, once continuous volcanic event, only became possible once the theory of plate tectonics achieved widespread scientific acceptance in the 1960s and 70s, providing geologists with the conceptual framework needed to mentally reassemble Pangea and recognize that basalt formations now separated by an entire ocean had, at the moment of their formation, been part of a single, continuous eruptive province. Radiometric dating techniques, refined considerably across the following decades, allowed researchers to establish with increasing precision that these geographically scattered basalts shared not just a common tectonic origin, but a remarkably tight shared age, all clustering within a narrow window around 201 million years ago. A level of temporal precision that made the connection to the Triassic-Jurassic extinction boundary, itself independently dated through fossil and sedimentary evidence, difficult to dismiss as mere coincidence. By the 1990s, the broad outline now familiar to paleontologists studying this boundary had solidified. A genuinely massive flood basalt province, its full extent finally appreciated once its scattered continental fragments were properly reassembled, erupting at essentially the same moment a major biodiversity crisis struck the planet. What remained elusive for another 3 decades was the fine-grained mechanistic detail. Not whether camp caused the extinction, which by this point few researchers seriously doubted, but precisely how, at what pace, and through which specific atmospheric pathway the eruptions translated into a catastrophe severe enough to eliminate 80% of the planet's species. This is where the story connects back to the broader revolution in geochemical analysis that has transformed paleoclimatology more generally over the past 2 decades. Mercury analysis as a tool for detecting ancient volcanic activity is a comparatively recent addition to the geochemist's toolkit, first developed and refined in earnest during the 2010s, initially applied to other extinction boundaries, most prominently the end Permian extinction and its associated Siberian traps volcanism, before researchers began systematically applying the same technique to the Triassic-Jurassic boundary. The specific innovation in the 2024 study was not the mercury technique itself, which by that point was reasonably well established, but rather the unusually high temporal resolution the research team achieved by sampling 6 geographically dispersed sedimentary sequences and cross-correlating their mercury signatures with independent astronomical dating methods, allowing them to resolve individual eruptive pulses within the broader 600,000-year camp sequence, with a precision measured in mere thousands, rather than tens of thousands, of years. This kind of precision matters enormously for distinguishing between a gradual greenhouse mechanism and a pulsed volcanic winter mechanism, because the 2 hypotheses make genuinely different predictions about the fine-scale timing of environmental disruption relative to the fine-scale timing of species disappearance in the fossil record. Predictions that simply could not be tested with the coarser dating resolution available to earlier generations of researchers working on this same boundary. It took, in the end, the convergence of several separate technical advances: high-precision radiometric dating, mercury geochemistry as an independent volcanic proxy, and increasingly detailed fossil occurrence databases, allowing researchers to track species disappearances with correspondingly fine temporal resolution. Before the specific, pulsed, sulfur-driven mechanism could finally be distinguished from the older, more general greenhouse narrative that had dominated the field for the previous 4 decades. There is something worth noting in the fact that Paul Olsen, one of the co-authors of the pivotal 2024 study, had already spent decades working specifically on the Newark Basin rift sequence in the eastern United States, one of the very same rift basins where dinosaur trackways document the late Triassic ecosystem functioning normally in the years immediately before the eruptions began. Researchers who spend an entire career returning to the same rock formations, generation after generation of published work, accumulate a depth of familiarity with the fine-scale stratigraphy that makes possible exactly the kind of high-resolution reanalysis that eventually overturned decades of established consensus. This is not a story of a single dramatic discovery arriving out of nowhere. It is a story of patient, cumulative expertise built up across an entire career studying a specific set of rock formations, finally combined with a genuinely new analytical technique to produce a result that changed how an entire scientific community understood one of the 5 most consequential extinction events in the history of life on this planet. A research team including scientists from Columbia University's Lamont Doherty Earth Observatory, publishing their findings in the Proceedings of the National Academy of Sciences in October of 2024, set out to measure mercury concentrations and mercury to organic carbon ratios across 6 geographically dispersed sedimentary records spanning the Triassic-Jurassic transition. Sites separated by thousands of kilometers, representing dramatically different ancient environments. From what were then continental interiors to shallow marine basins. Their goal was to determine, with a level of temporal resolution no previous study had achieved, exactly how the intensity of camp volcanism was distributed across its 600,000-year eruptive history. Whether the eruptions had proceeded as one long, relatively steady outpouring of lava and gas, or whether the volcanic activity had instead arrived in sudden, concentrated bursts. What the mercury data revealed was the second scenario, and it changed everything about how researchers needed to think about the extinction's actual mechanism. The eruptions were not steady. They were pulsed, arriving in a series of intense, geologically brief episodes, each one separated from the next by quieter intervals, rather than unfolding as one continuous, gradually building event. And critically, the very first and most concentrated pulse of camp volcanism, the initial eruptive episode, precisely coincident with the onset of the mass extinction in the fossil and sedimentary record, appeared to have released a genuinely staggering quantity of sulfur into the atmosphere in a remarkably short span of geological time. According to the study's findings, this initial pulse released more than 500 times the amount of sulfur that was emitted during the 1991 Pinatubo eruption. 500 times the sulfur that cooled the entire planet by half a degree for a full year. Released not across a single event, but across a series of repeated injections occurring in rapid succession, compressed into a period the researchers describe as subcentennial in scale, meaning these individual pulses of intense sulfur release may have occurred within spans of less than 100 years each, hammering the atmosphere with sulfate aerosols again and again, before the previous pulse's cooling effects had even fully dissipated. This is the mechanism that overturned the old model. A greenhouse-driven extinction, unfolding gradually as carbon dioxide slowly accumulated over hundreds of thousands of years, would predict a world that grew steadily, if unevenly, warmer across the extinction interval. A slow-motion catastrophe with a relatively gentle onset. What the sulfur data instead pointed toward was something far more abrupt and far more violent. Repeated, severe volcanic winters, each one triggered by a massive pulse of sulfate aerosols blocking incoming sunlight, each one capable of driving global and especially continental interior temperatures down dramatically and rapidly, in a pattern of cooling shocks striking the biosphere again and again, over a geologically brief window at the very start of the eruptive sequence, precisely the same window during which the extinction itself appears in the fossil record to have struck hardest. As Paul Olson, a paleontologist at Lamont Doherty and a co-author of the study, put it in discussing the findings, the magnitude of environmental effects produced by an eruption is related to how concentrated the eruptive events are in time. A given total volume of sulfur released gradually over a long interval allows a planet's climate system time to buffer and adjust. That same volume, released in a handful of sudden overlapping pulses within a span of decades to centuries, does not permit any such buffering. It hits the biosphere like a hammer blow, repeated before the wound from the last strike has had any chance to heal. Consider what a volcanic winter of this intensity would have actually meant, physically, for the late Triassic world. Sulfate aerosols in the stratosphere do not distribute their cooling effect evenly across the planet's surface. Continental interiors, regions far from the moderating thermal influence of the ocean, cool far more severely and far more rapidly than coastal areas or the oceans themselves. Because water retains heat far longer than land and buffers temperature swings that land surfaces cannot resist. And Pangea, remember, was overwhelmingly continental interior. Vast stretches of that single unified supercontinent sat thousands of kilometers from any coastline. When the sulfate veil settled over the stratosphere, blocking a significant fraction of incoming sunlight, these interior regions would have experienced cooling far beyond what the already substantial half-degree global average Pinatubo produced, plausibly a swing severe enough to bring genuinely freezing conditions, sustained over months or years at a time, into regions of the supercontinent that had never previously needed to cope with sub-freezing temperatures at any point in their recent evolutionary history. For an ectothermic reptile, an animal that generates little or no internal metabolic heat and depends entirely on ambient environmental temperature to regulate its own body functions, a sudden, sustained collapse into freezing conditions across a landscape with no prior experience of such cold represents a catastrophe with almost no available biological response. There is no behavior available, no physiological adjustment achievable on any timescale shorter than many generations that allows a large-bodied, heat-adapted reptile to simply cope with genuine winter cold, arriving without warning across the heart of its home range. The Rauisuchians, the Artosaurs, the Phytosaurs, whose river-dwelling ambush lifestyle depended on liquid water and warm-blooded prey remaining active and accessible year-round. These were animals whose entire evolutionary history, across tens of millions of years, had unfolded within the thermal envelope of Pangea's warm, stable, tropical and subtropical interior. They had never needed cold tolerance. Evolution had never selected for it, because the ecological conditions that would have made cold tolerance valuable had simply never existed within their world. And this is the precise point at which the story returns to the detail we set aside earlier. The dinosaur populations already living at the high latitude margins of the supercontinent, in regions that, even under the Triasic's generally warm greenhouse climate, experienced genuine seasonal cold and extended periods of winter darkness at their extreme latitudes. These populations were not thriving in the sense of ecological dominance. They were marginal, restricted to environments the larger pseudo-Suchian competitors found unappealing or physiologically difficult to exploit. Smaller in body size, feathered in at least some documented cases, adapted through tens of millions of years of ordinary evolutionary pressure to tolerate cold, low-light conditions that would have been irrelevant, even meaningless, to a heat-loving predator patrolling the tropical rivers of Pangea's interior. When the volcanic winters struck, these were not new adaptations hastily improvised in response to catastrophe. They were pre-existing traits, already fully evolved, already functioning, simply waiting, without any foresight, without any biological intention, for a set of environmental conditions that would suddenly make them the difference between extinction and survival. This is not a story about the fittest surviving in any morally weighted sense. It is a story about a pre-existing trait, evolved for entirely unrelated reasons across millions of years of ordinary marginal existence, at the cold edges of a supercontinent, turning out by pure evolutionary contingency to be exactly the trait a sudden global catastrophe would select for. The dinosaurs did not become cold tolerant because a volcanic winter was coming. They happened to already be cold tolerant when it arrived, and that accident of prior evolutionary history is, according to the current evidence, a central reason they were still present in meaningful numbers on the other side of the extinction event, while so many of their larger, more thermally specialized Triassic competitors were not. The fossil record across the Triassic-Jurassic boundary bears this pattern out with striking clarity. In sediment layers immediately below the camp eruptive horizon, researchers find a diverse Triassic fauna, large terrestrial and semi-aquatic relatives of crocodiles, unusual tree-dwelling lizards, giant flat-headed amphibians, alongside a rich diversity of tropical plant life adapted to the warm, stable conditions that had prevailed for millions of years. Moving upward through the rock layers that correspond to the eruptive interval itself, this diversity collapses. Many of these lineages simply disappear from the fossil record, their final occurrences clustering tightly around the same horizon where the mercury spikes indicating the most intense volcanic pulses are also found. And then, in the layers above, in rock representing the recovery period following the eruptions and extending into the early Jurassic beyond, a different fauna begins to dominate. Small, feathered dinosaurs, turtles, true lizards, early mammals, animals that, on the whole, shared one broad characteristic in common. They were comparatively small, and at least some among them, the dinosaur lineage chief among them, carried inherited cold tolerance from ancestors who had spent generations at the thermal margins of the world that had just been so violently disrupted. Body size itself appears to have mattered as much as latitude of origin. Smaller animals, across the board, seem to have fared measurably better through the extinction interval than their larger counterparts. And the proposed explanation connects directly back to the same volcanic winter mechanism. Small-bodied animals capable of sheltering in burrows, in crevices beneath fallen vegetation, or in other forms of physical refuge, could escape at least some portion of the most extreme surface temperature swings that a sudden volcanic winter would have imposed, buffering themselves, however imperfectly, against conditions that a large, exposed animal patrolling open terrain had no comparable means of avoiding. This may help explain why turtles, lizards, and early mammals, groups whose members tended, at this point in their evolutionary history, toward comparatively modest body sizes, also persisted successfully across the boundary alongside the surviving dinosaur lineages. While so many of the largest Triassic reptiles, animals built at a scale that made any form of physical shelter-seeking essentially impossible, did not. Everything discussed so far has concerned the terrestrial side of this extinction, the reptiles of Pangea's interior, the volcanic winters that reshaped their world. But the Triassic-Jurassic extinction was not a land-only event. It struck the oceans with, if anything, even greater severity. And the marine record of this catastrophe tells a story that runs in parallel to the terrestrial one, while adding an entirely separate dimension to the mechanism now understood to be responsible. Ammonites, coiled, shelled cephalopods related to modern squid and octopus, but encased in an external shell divided into gas-filled chambers used for buoyancy control, had been one of the most successful and diverse groups in the Triassic Ocean, filling ecological roles ranging from small filter-feeding drifters to substantial active predators. Across the Triassic-Jurassic boundary, ammonite diversity collapsed catastrophically. Multiple entire ammonite families, some of which had persisted through earlier crises with little difficulty, disappear from the fossil record within a geologically narrow window, tightly correlated with the camp eruptive interval. The survivors that did make it through the boundary appear to represent a tiny, bottlenecked remnant of the group's former diversity, a handful of lineages from which the entire subsequent Jurassic and Cretaceous ammonite radiation, one of the most spectacular examples of evolutionary recovery and diversification in the fossil record, would eventually descend. Conodonts, an enigmatic group of small, eel-like marine animals known primarily from their distinctive tooth-like phosphatic elements, which had served paleontologists as remarkably precise index fossils for dating marine rock layers across more than 300 million years of Earth history, vanish entirely at the Triassic-Jurassic boundary. Not diminished, not reduced to a marginal presence, extinct, completely and permanently, after having survived every previous mass extinction in the geological record up to that point, including the catastrophic end Permian event tens of millions of years earlier. Whatever ecological or physiological vulnerability conodonts carried, it proved fatal precisely at this boundary and at no earlier crisis in their long evolutionary history. A detail that itself suggests something specific and unusual about the particular character of this extinction event, distinct from the mechanisms responsible for earlier catastrophes. These same animals had weathered successfully. Reef ecosystems suffered perhaps the most visually dramatic collapse of all. Triassic reefs, built primarily by an unusual group of bivalves and by early scleractinian corals, the same broad coral lineage responsible for modern reef systems today, had achieved substantial ecological complexity and geographic extent across the shallow tropical seas bordering Pangea. Across the extinction interval, reef building essentially stopped worldwide. Geologists refer to the several million-year interval immediately following major extinctions during which reef ecosystems failed to re-establish as a reef gap, and the reef gap following the Triassic-Jurassic boundary is one of the more pronounced examples documented anywhere in the geological record, with robust, ecologically complex reef systems not reappearing in the fossil record for a span of time that, by some estimates, stretches several million years into the early Jurassic. The proposed mechanism connecting these marine losses to the same volcanic activity responsible for the terrestrial extinction runs through ocean chemistry rather than temperature directly, though the two are not unrelated. Carbon dioxide released across the full 600,000-year eruptive history of Camp, even if it was not the primary driver of the sharpest initial extinction pulse on land, did steadily dissolve into the world's oceans, forming carbonic acid and gradually lowering ocean pH in a process directly analogous to modern anthropogenic ocean acidification, just operating across a dramatically longer timescale, and, ultimately, reaching a considerably more severe endpoint. Marine organisms that build shells or skeletons from calcium carbonate, ammonites, reef-building corals and bivalves, and countless other Triassic marine invertebrates become measurably less able to construct and maintain those calcified structures as ocean pH declines, since the chemical reactions required to precipitate calcium carbonate from seawater become progressively less energetically favorable under more acidic conditions. Sedimentary evidence from Triassic-Jurassic boundary sections in locations including the United Kingdom and Austria shows geochemical signatures consistent with a genuine ocean acidification event unfolding across this same interval, adding a slower acting but no less consequential dimension to a catastrophe that on land arrived largely as a series of sudden cooling shocks. The combined picture that emerges from integrating the terrestrial and marine records then is not a single simple mechanism but a compound catastrophe. Sudden, repeated volcanic winters striking the land with brutal speed, layered atop a slower, more gradually building ocean acidification crisis. driven by the same eruption's cumulative carbon dioxide output, both mechanisms tracing back to the identical geological event, both leaving their own distinct signature in the rocks, and both converging to produce, across land and sea alike, one of the 5 most severe biodiversity crises this planet has ever experienced. The plant fossil record across this boundary offers its own distinct line of evidence, entirely independent of the vertebrate bones and marine shells discussed so far. And it tells a remarkably consistent story of sudden, severe ecological disruption. Palynologists, researchers who specialize in studying fossil pollen and spores, microscopic and remarkably durable structures that accumulate in enormous quantities within sedimentary rock and can be extracted, identified, and counted with considerable precision, have documented a dramatic shift in plant community composition precisely at the Triassic-Jurassic boundary, occurring in sedimentary sections on multiple continents, with a consistency that mirrors the vertebrate turnover happening in the same rock layers. Immediately below the boundary, pollen assemblages reflect a diverse late Triassic flora, dominated by conifers, cycads, and seed ferns, adapted to the warm, strongly seasonal monsoonal climate of Pangea's interior. At the boundary itself, in section after section around the world, this diverse assemblage gives way abruptly to what palynologists term a fern spike, an extraordinary, short-lived surge in fern spore abundance, sometimes representing more than 90% of the total pollen and spore assemblage in the most extreme samples, before more typical plant community diversity gradually reasserts itself over the following tens of thousands of years. This pattern will be familiar to anyone who has studied other major extinction boundaries in Earth's history, because a strikingly similar fern spike appears at the Cretaceous-Paleogene boundary 66 million years later, in sediments immediately overlying the layer marking the Chicxulub asteroid impact. Ferns, as a botanical group, are opportunistic colonizers, fast-growing, capable of rapidly recolonizing disturbed or devastated landscapes, from wind-dispersed spores long before slower-growing trees and shrubs can re-establish themselves. A fern spike, in the language of paleobotany, is essentially a signature of ecological catastrophe. A landscape stripped bare of its established plant communities, being recolonized in a hurry by whatever species can grow fastest in the immediate aftermath. Alongside the fern spike, researchers studying Triassic-Jurassic boundary sections have documented something considerably stranger: a pronounced spike in fungal spores, in some locations accompanied by unusual, malformed pollen grains showing developmental abnormalities consistent with severe environmental stress during the plant's reproductive development. This fungal spike has been interpreted as evidence of widespread plant dieback, dead and dying vegetation across the landscape, providing an abundant substrate for decomposer fungi to exploit, at a scale far beyond what ordinary background ecological turnover would produce. Taken together, the fern spike, the fungal spike, and the malformed pollen grains paint a picture of terrestrial plant communities experiencing acute, widespread stress and mortality, precisely coincident with the interval identified by the mercury data as the most intense pulse of camp volcanism. Vegetation collapsing under conditions that, given everything already established about the volcanic winter mechanism, were almost certainly driven by the same sudden loss of sunlight and dramatic cooling responsible for the vertebrate extinction pattern discussed earlier. This plant evidence matters for more than simply corroborating the broader extinction narrative from an independent angle, though it does that as well. It also helps explain part of the mechanism by which surviving animal populations experienced the crisis. Because a sudden, severe disruption to plant communities represents a collapse of the entire terrestrial food web's foundation. Herbivorous animals, whatever their thermal tolerance, faced a landscape in which their food supply had been catastrophically disrupted at precisely the same moment temperatures were plunging. A compounding crisis in which the direct physiological stress of extreme cold was accompanied by the indirect but equally severe stress of starvation, as familiar food sources died back or failed to grow. Any surviving lineage needed not only cold tolerance, but also sufficient dietary flexibility or metabolic reserve to weather a period during which the plant base of the ecosystem was itself in active collapse. An additional layer of selective pressure operating alongside and likely reinforcing the direct thermal filtering already discussed. What followed, once the initial volcanic pulses subsided and the camp eruptive sequence gradually wound down across its remaining several 100,000 years, was not an immediate return to normalcy. Ecosystems that have absorbed a shock of this magnitude do not simply reset. But the ecological space that had, for tens of millions of years, been occupied and effectively monopolized by the Pseudo-Suchian lineages was now, in the most literal biological sense, empty, vacated by extinction, available to any surviving lineage capable of expanding into it. Dinosaurs, having survived the extinction interval in meaningful numbers where so many of their former competitors had not, were positioned to do exactly that. Across the following several million years of the early Jurassic, the fossil record documents a dramatic expansion, not merely in the number of dinosaur species present, but in their body size, their ecological diversity, and their geographic range. As lineages that had spent the preceding tens of millions of years as a marginal, ecologically constrained presence, began for the first time to occupy the large-bodied predator and large-bodied herbivore niches that Pseudo-Suchian reptiles had previously controlled almost entirely. This expansion did not happen instantly, and it did not happen everywhere at once. But by the middle of the Jurassic period, the ecological transformation was essentially complete. The world that had, for the entire span of the Triassic, belonged to crocodile-line reptiles now belonged, comprehensively, and for the next 135 million years, to dinosaurs. It is worth tracing the dinosaur radiation that followed this extinction in somewhat more specific detail, because the sheer speed and scale of the transformation, once it began, deserves more than a general summary. In the immediately post-extinction earliest Jurassic, dinosaur body sizes remained relatively modest, continuing the pattern already established in their marginal Triassic existence. Fossils from this interval recovered from formations including the early Hatangian Age rocks of South Wales and the American Southwest, document small to mid-sized theropods and early sauropodomorphs occupying ecological space that, only a few 100,000 years earlier in geological terms, had still belonged to the last surviving Pseudosuchian lineages clinging on in the immediate aftermath of the volcanic winters. The transformation accelerated dramatically within the following several million years. Sauropodomorph dinosaurs, the lineage that would eventually produce the truly gigantic long-necked sauropods of the Middle and Late Jurassic, began a sustained trajectory of body size increase almost immediately after the extinction boundary, a pattern documented with unusual clarity in the fossil record of Southern Africa and South America, where relatively continuous rock sequences spanning the earliest Jurassic preserve a step-by-step record of sauropodomorph lineages growing progressively larger across successive rock layers. Within perhaps 10 to 15 million years of the extinction, a remarkably short interval by the standards of major evolutionary transitions, early sauropodomorph descendants had already begun to exceed the maximum body sizes achieved by any Pseudosuchian predator or herbivore. During the entire preceding Triassic period, a threshold that took the crocodile-line reptiles tens of millions of years to establish, and that dinosaurs surpassed in a fraction of that time once the ecological space became available to them. Theropod dinosaurs underwent a parallel transformation on the predatory side of the ecosystem. Early Jurassic theropods like Dilophosaurus, known from well-preserved fossils in Arizona and dating to within a few million years of the extinction boundary, already show a substantial increase in body size and predatory specialization compared to their Triassic Age ancestors, reaching lengths of 6 meters or more, squarely within the size range previously occupied by Rauisuchian apex predators, now filled by an entirely different reptilian lineage operating with a broadly similar ecological strategy, but a genuinely distinct evolutionary history. By the Middle Jurassic, only 20 to 25 million years after the extinction event, theropod diversity had expanded to include the direct ancestors of the megalosaurs and the earliest members of the lineage that would eventually produce Allosaurus, establishing the basic predatory guild structure that would persist, with modification, for the remainder of the Mesozoic era. This transformation extended beyond simple increases in size. The ecological range dinosaurs came to occupy expanded dramatically as well, into niches the group had never previously exploited during its marginal Triassic existence. Ornithischian dinosaurs, the lineage that would eventually produce the horned, armored, and duck-billed dinosaurs so familiar from later Mesozoic ecosystems, remained a comparatively minor presence immediately after the extinction, but began their own diversification across the early and middle Jurassic, gradually establishing the herbivorous body plans and feeding strategies that would eventually allow the group to become one of the most successful and diverse dinosaur lineages of the Cretaceous period. What had been, throughout the entire span of the Triassic, a single ecologically marginal, cold-tolerant lineage, restricted largely to the thermal margins of Pangea, had become, within a geologically brief interval of perhaps 20 million years, the dominant vertebrate group across essentially every terrestrial ecosystem on the planet, occupying the large predator niche, the large herbivore niche, and a rapidly expanding range of smaller-bodied ecological roles. Besides, a transformation whose speed becomes considerably more remarkable once you hold in mind that its entire foundation rests on a volcanic winter that, in absolute terms, may have struck and receded within less than a single human lifetime. There is a particular kind of vertigo available in sitting with how contingent this outcome actually was. The extinction that opened this door was not, on the evidence currently available, driven by the mechanism researchers assumed for decades, a slow, grinding greenhouse catastrophe that any sufficiently heat-tolerant lineage might reasonably have been expected to weather. It was driven, instead, by something closer to the opposite, a series of sudden, violent cooling shocks, arriving with a speed and intensity that offered almost no opportunity for adaptation within the time frame available, and that specifically and disproportionately punished exactly the trait, heat specialization, honed across tens of millions of years of stable tropical dominance, that had made the pseudo-Suchian lineages so ecologically successful in the first place. The very adaptation that had allowed Rawisuchians and their relatives to dominate Pangea's warm interior for so long became, in the span of what may have been mere decades, the precise vulnerability that ended them. And the animals that inherited the planet did not do so because of any adaptation specifically evolved in anticipation of catastrophe. They inherited it because of a trait that had originated as an unremarkable, ecologically marginal accommodation to a cold, unglamorous corner of the world. A trait that had never been, in any meaningful evolutionary sense, aimed at anything at all, until a volcanic winter arrived, and for reasons no dinosaur population could have possibly anticipated, made that trait the single most valuable inheritance an animal could carry into the Jurassic. This reversal, heat as vulnerability, cold as unlikely salvation, is precisely the kind of finding that should make anyone genuinely curious about deep time pause and reconsider how confidently we narrate these ancient catastrophes. For nearly 4 decades, the greenhouse extinction model for the Triassic-Jurassic boundary was not a fringe position. It was the mainstream, textbook explanation, taught with real confidence, built on genuine and substantial evidence regarding the relationship between flood basalt volcanism and atmospheric carbon dioxide. It was not wrong because the underlying chemistry was flawed. Carbon dioxide from camp almost certainly did contribute to longer-term warming and ocean acidification stress across the extinction interval and its aftermath. The new mercury-based sulfur findings do not erase that longer-term greenhouse signal, so much as reveal that it was not, in fact, the dominant proximate mechanism driving the sharpest, most concentrated pulse of extinction at the very start of the eruptive sequence. The model was incomplete, not incorrect, missing a piece of the mechanism that required an entirely different analytical approach, focused on a different trace element entirely, to finally bring into view. There is a broader pattern worth drawing out here, one that extends well beyond this single extinction event, and touches something close to the central intellectual project of studying deep time at all. Every one of the 5 major mass extinctions currently recognized in the geological record has, at one point or another, been explained by scientists with a confidence that later evidence complicated, revised, or in some cases overturned outright. The end Permian extinction, the most severe crisis in the history of complex life, was for decades attributed primarily to the Siberian Traps eruptions in a relatively straightforward greenhouse warming narrative, before subsequent research revealed a far more tangled sequence of ocean anoxia, hydrogen sulfide poisoning, and ozone layer collapse operating in combination. The end Cretaceous extinction, popularly remembered as a simple asteroid story, continues to generate genuine scientific debate over the relative contribution of the Chicxulub impact versus the Deccan Traps volcanism that was already underway when the asteroid struck. Deep time, it turns out, rarely offers the tidy, single-cause narratives that make for satisfying stories. It offers, instead, compound catastrophes, overlapping mechanisms, and explanations that shift meaningfully as analytical techniques improve. The mercury-based sulfur discovery discussed throughout this film exemplifies exactly this pattern of revision. And it is worth being honest about what that pattern actually implies for how confidently any of us, including the researchers who study this material for a living, should hold on to the current best available explanation for any given ancient catastrophe. The greenhouse extinction model for the Triassic-Jurassic boundary was not built on sloppy science. It was built on real evidence, interpreted reasonably, using the best analytical tools available at the time, by researchers operating in good faith and genuine expertise. It held up reasonably well in broad outline for the better part of 4 decades. And it was still, in a specific and consequential way, incomplete, missing a mechanism that required looking at an entirely different trace element, using techniques that simply did not exist in a practically applicable form until relatively recently, to finally bring into focus. This should not be read as evidence that science cannot be trusted, or that today's explanation will inevitably be overturned tomorrow in some endless, directionless cycle of revision. The opposite is closer to the truth. Each revision of this kind represents genuine accumulated knowledge. The newer sulfur-based model does not discard the earlier carbon dioxide evidence. It incorporates it into a more complete and more precisely timed picture of what actually happened, integrating 2 previously separate lines of evidence into a single, more accurate account. This is what scientific progress on questions of deep time actually looks like in practice. Not a series of complete reversals, but a slow, patient tightening of the picture. Each new technique adding resolution that the previous generation of researchers simply did not have access to, gradually converging on an account that grows more detailed and more mechanistically precise with each subsequent study. Even as the broad outline, a massive volcanic province, a severe global extinction, a subsequent ecological transformation, remains essentially stable across the entire process. What remains at the end of this particular story is a question worth sitting with directly rather than resolving too quickly. The reign of the dinosaurs. 135 million years of ecological dominance, encompassing everything from the earliest small Jurassic theropods to the titanic sauropods of the late Jurassic, to the final flowering of diversity in the late Cretaceous, immediately before the Chicxulub impact, exists on the evidence currently available, because a lineage of small, unglamorous reptiles happened to have already evolved cold tolerance for reasons that had nothing whatsoever to do with anticipating a catastrophe. Tens of millions of years before any volcanic winter arrived to make that particular trait suddenly, decisively valuable. There was no foresight in this. There was no trajectory bending toward an inevitable dinosaurian future. There was, instead, a supercontinent that happened to be rifting apart at a particular geological moment, releasing sulfur in pulses concentrated across a span of decades to centuries rather than spread evenly across hundreds of thousands of years, striking a world in which one lineage, entirely by accident of where its marginal populations happened to be living, already carried the one adaptation that mattered most when the sky went dark and the temperature dropped. There is a final dimension to this research worth addressing directly, because it explains why paleoclimatologists studying an event 200 million years in the past have attracted genuine attention from researchers whose primary concerns are considerably more immediate. Volcanic winters are not purely historical curiosities confined to deep time. They represent a recognized category of climate risk that modern volcanology and climate science continue to study actively, precisely because the underlying physical mechanism, sulfate aerosols injected into the stratosphere, reflecting incoming sunlight and driving rapid global cooling, remains exactly as available to a sufficiently large modern eruption as it was to Camp 201 million years ago. The Tambora eruption of 1815 in what is now Indonesia remains the most severe volcanic winter documented within recorded human history, releasing enough sulfur dioxide into the stratosphere to produce what became known across the northern hemisphere as the year without a summer. Widespread crop failures across Europe and North America, snowfall recorded in New England during the month of June, and famine conditions severe enough to contribute to documented social and political upheaval across multiple continents. Tambora's eruption, by most estimates, released perhaps 60 million tons of sulfur dioxide, roughly 3 times the Pinatubo eruption, and still a small fraction of the 500 times Pinatubo figure now associated with Camp's initial pulse. The fact that an eruption several orders of magnitude smaller than a single Camp pulse could still produce measurable global famine and social disruption within recorded human history offers a sobering point of calibration for imagining what repeated eruptions at Camp's documented scale would have meant for ecosystems entirely unprepared, over evolutionary or cultural timescales, for anything resembling that level of disruption. Researchers studying large igneous provinces like Camp increasingly frame this work as directly relevant to understanding the upper bound of volcanic climate risk facing the modern world. since several volcanic systems capable of producing eruptions substantially larger than any documented within human history remain geologically active today, even if none currently show evidence of building toward anything approaching Camp's documented scale. Understanding precisely how quickly and through which specific atmospheric pathway a large-scale eruption translates into severe, biosphere-altering climate disruption is not simply an exercise in reconstructing an ancient catastrophe for its own sake. It is, increasingly, treated by the broader scientific community studying planetary-scale hazards as a genuinely useful natural experiment, one already conducted by the planet itself, its results permanently recorded in rock and available for study, offering insight into questions about volcanic climate forcing that no modern researcher would ever be able to test through direct observation or controlled experiment. This is, perhaps, the final and most quietly consequential dimension of a story that began 201 million years ago and appeared for decades to be a settled, closed chapter of deep Earth history. It is not closed. It continues to be actively studied, actively revised, and increasingly understood as directly relevant to questions about the physical limits and mechanisms of planetary-scale climate disruption that extend well beyond the specific fate of late Triassic reptiles. A 200-million-year-old catastrophe still, in a very real sense, teaching researchers something new about how this planet's atmosphere responds to the largest disruptions its own interior is capable of producing. Run the tape again, as the paleontologist Stephen Jay Gould once famously suggested, as a thought experiment for exactly this kind of question. And there is no particular reason to expect the same outcome. Shift the timing of Camp's initial eruptive pulse by even a few 100,000 years. Before dinosaur populations had established themselves as firmly at high latitudes and an entirely different lineage, perhaps some as yet undiscovered branch of the Pseudosuchians, perhaps something else altogether, might have inherited the empty ecological space left behind by the extinction, and the entire subsequent history of vertebrate life on this planet, all the way up through the eventual evolution of mammals, and eventually of the species reading these words right now, might have unfolded along a completely different trajectory. We exist, in some very real sense, downstream of a volcanic winter that happened to arrive at precisely the geological moment it did, striking a world in which cold tolerance happened. By pure evolutionary accident, to already be sitting at the margins, waiting for exactly the catastrophe that would make it matter. This point about compound, overlapping mechanisms deserves one further illustration, because it clarifies why researchers were initially so reluctant to abandon the greenhouse model, even as the sulfur evidence accumulated. Extinction events of this magnitude rarely trace back to a single, isolated cause acting in complete independence from every other environmental stressor unfolding at the same time. The late Triassic biosphere entering this crisis was not a naive, unstressed system encountering its first environmental challenge in isolation. Ocean chemistry had already been shifting gradually in the millions of years leading up to the boundary, and background rates of species turnover show some evidence of elevated stress even before the first camp pulse arrived. The volcanic winters described throughout this film functioned, in this sense, less like a bolt from a clear sky, and more like the final, decisive blow delivered to a biosphere that may have already been operating with reduced resilience. Its buffering capacity against sudden shocks, already somewhat diminished by longer-term environmental trends that current research continues to investigate. This does not diminish the significance of the sulfur-driven volcanic winter mechanism as the proximate, decisive trigger. The timing correlation between the initial camp pulse and the sharpest extinction signal remains remarkably precise. But it is a useful reminder that even the most dramatic single-event explanations in the history of life on Earth tend, on sufficiently close inspection, to reveal themselves as the culmination of multiple interacting pressures, rather than a single, clean and isolated cause. That is not a comforting thought, in the sense of offering any grand design or inevitable direction to the history of life on Earth. But it is, perhaps, a genuinely clarifying one. The story of how cold created the reign of the dinosaurs is not a story about destiny. It is a story about contingency operating at a planetary scale, about how the deep, patient, indifferent machinery of plate tectonics, entirely unconcerned with the biological consequences of its own operation, can reach up from the mantle and rewrite, within the span of a few short centuries, which lineages get to inherit the next 135 million years of this planet's history.